Basic set concepts. Define sets. A set is a collection of distinct, well-defined objects or elements. The roster method of representing sets separates the elements of the set with commas and places them in curly brackets. Well-defined means that it should be unambiguous whether an object is an element of a set or not. For example, the collection of the best days of the week is not a well-defined set because of the ambiguous nature of the word best. On the other hand, the collection of days of the week whose spelling contains the letter S is well-defined because we can go through the names of the days of the week and only include the ones that have the letter S. This set can be represented in roster form. We'll call it set A, and let's see, is Monday in the set? No, Monday doesn't have an S. Tuesday is in the set, so is Wednesday, so is Thursday. Friday doesn't have an S. Saturday is in the set, and Sunday is in the set. So this is a list of the days that have the letter S in their spelling. Well-defined set. All right, now let's take a look and see if we can't determine this well-defined set. It's the set of letters in the word transition. We'll call this set A. So let me see. We'll go through. Is the letter A in the set? A is in the set. So we'd have the letter A there. Is the letter B in the set? Well, the letter B is not in the word transition, so it's not in the set. If you go through the entire alphabet, you'll come up with this list. This is the list of letters that are in the word transition. And as we went through the 26 letters, it was obvious whether or not the letter should be included in the set. So this is a well-defined set. All right, here's another well-defined set. The set B of even numbers between 5 and 19. So between 5 and 19, we have 6 is even, 7 is not. 8 is even, 9 is not. 10 is even, and so forth. We go all the way up to 19. We'll come up with this list of numbers, and each number we go through between 5 and 19 should be obvious whether it's even or not, and whether or not it goes into this set. So this is another well-defined set. Here's another well-defined set, the set of basic primary colors. So the set of basic primary colors consists of red, yellow, and blue. These are the basic primary colors. So these are some well-defined sets. It's obvious whether or not an object is in the set or is an element of the set. All right, now let's define the cardinality of a set. The cardinality of a set is the number of elements in the set. A finite set is a set with a fixed number of elements, or a finite cardinality. The cardinality of a finite set A is denoted NA. So when you see this, you can read this as the cardinality of A or the number of elements in set A, either way. So given set A, so this is that same set of letters in the word transition, find the number of elements in set A. So that's what this symbol means. When you see N with parentheses and then a capital letter inside, or the letter that represents a set inside, I should say, then that just means how many elements are in this set. So we count 1, 2, 3, 4, 5, 6, 7 elements in the set. So the cardinality of the set is 7. And we denote that NA, the cardinality of set A is 7. All right, let's look at another set. This is the set of even numbers between 5 and 19. So let's see. It's asking us to find N of B, or the cardinality of that set. So we're asked to find the number of elements in this set. 1, 2, 3, 4, 5, 6, 7. So this set also has 7 elements. So these two sets, they have the same number of elements. All right, last set on this page at least. Set C, the set of the basic primary colors. And this set has 1, 2, 3 elements. The 3 colors red, yellow, blue. So the cardinality of that set is 3. Now you notice that set A and set B have the same cardinality. There's a name for that. 2 sets that have the same cardinality or the same number of elements are called equivalent sets. So they're not equal to each other because obviously one contains letters, the other one contains numbers. So they're not equal to each other, but because they have the same number of elements, they are equivalent to each other. So let's look at 2 more sets here. Let's look at this set D. And this set D contains the element 0, the number 0. So it asks us to find the cardinality of set D, or the number of elements in set D. Now set D has 1 element, the number 0 in it. So the cardinality of set D is 1. Now let's take a look at a special set. This set has its own special symbol. So given the empty set, and the empty set has this symbol to use to denote it, the empty set is a set that has no elements. So you notice the curly brackets, there's nothing on the inside. When there's nothing on the inside, that means there's no element for this set. So the cardinality of the empty set is 0. The number of elements in the empty set is 0. Okay, that is something very specific, something you'll want to remember. The set containing no elements is called the empty set or the null set, and the cardinality of the empty set is 0. So any set that has an element at all is not the empty set. If it has an element in it, it's not the empty set. The only set that has a cardinality of 0 is this empty set. Okay, now we can use ellipses to show patterns when we're using set builder notation. So for larger sets, ellipses can be used to indicate that the pattern continues. For finite sets, write the first 3 elements of the set, then write the ellipses, then write the last element of the set. Finally, enclose this all within curly brackets. So let's do that. Write the set of months of the year in roster form. So we're going to use these ellipses instead of listing all the months of the year. So what are we going to do? Well, let's call this set E, and we're going to list the first 3 months of the year like it says to do. Write the first 3 elements of the set. Then we're going to put the ellipses. Here are the ellipses, those 3 dots. And then we're going to write the last element of the set, which is December. That's the last month of the year. And finally, it's all enclosed within curly brackets. So that's proper set builder notation. I use the ellipses correctly to show that after January, February, March, I continue with that pattern until I get to December. That's what those ellipses mean. All right, let's do that one more time. So write the set of even numbers between 1 and 100 using the roster method. Okay, so this set, let's call it F, and I'll list the first 3 elements first. So between 1 and 100, the even numbers, 2, then 4, then 6. Those are the first 3 even numbers after 1. And then you put the ellipsis, and then the last even number before 100 is 98. So that's the last even number that would be between 1 and 100 would be 98. So this list represented using roster form and ellipsis. All right. These are both finite sets. Let's talk about how to use these ellipses with infinite sets. So ellipses can also be used to represent infinite sets that have an unlimited number of elements. So we're going to have an infinite number of elements in these infinite sets. First, we'll write the set of positive counting numbers. So the set of positive counting numbers, when you're counting, you start with the number 1. That's the smallest counting number. Then you go on to 2 and 3 and so forth. So to represent that using roster form, well, there's a special symbol that we use for this set, is this special N. So whenever you see this special N, they're talking specifically about this set. 1, 2, 3. You put the ellipses to show that continues as a pattern, but then you don't put anything on the right side of the ellipses to show that pattern continues forever. This special set is called the set of natural numbers. So whenever you see this symbol, it represents the set of natural numbers, which are just the numbers we use to count. There's an infinite number of those. There's no end to counting. Like, you can't count to the largest number. That's what infinity kind of represents. So let's write the set containing the positive and negative counting numbers and 0 using the roster method. So we're going to have the positive counting numbers, which we already have here. The negatives of these, the negative counting numbers, which are just these but negative. And 0 all in one set. And here's what that set looks like. It also has a special symbol to represent it. It's this fancy Z. And this set also has a special name. It's called the set of integers. So this is the set of integers. So this is how we use roster notation. There's another notation we can use to represent sets. That notation is called set builder notation. Set builder notation is a shorthand way to write sets, and it uses a verbal description or a formula for the set. Set builder notation consists of the curly brackets, so regardless of how you're representing the set, you need the curly brackets, inside of which there is a vertical line. On the left of the vertical line is a variable, and on the right of the vertical line, there is a rule that returns elements of the set or a logical formula that evaluates to true for any elements of the set. So on the right side, there'll either be a formula that when you plug something in, you get elements of the set, or some logical thing that when you evaluate it, if it's true, whatever you plugged in is an element of the set. All right, so here's an example here. Write the set F of these elements using set builder notation. So this is the roster form. This seems to be just the natural numbers up to 150, because it's 1, 2, 3, and then ellipses, meaning you continue counting with just the counting numbers, but then it ends at 150. So if we're going to write that using set builder notation, we'll have the curly brackets, we'll have a vertical bar. On the left of the vertical bar, we have the variable we want to use. We want to use the variable x. So the elements are going to be whatever x is equal to. Now x is an element of the natural numbers. So x is automatically a natural numbers because it says that x is in the natural numbers, and also x is less than or equal to 150. So this describes these numbers. This is a description of the type of numbers that are in this set. So this is the set builder notation. You start off with the curly bracket, you put the variable that you want to represent the elements of the set with, and then you describe the variable. You describe characteristics of the variable using notation here. So x is an element of the natural numbers, so that narrows it down to just the counting numbers. But I also narrow it down by saying it has to be a counting number that's less than or equal to 150. All right, here's another one. Write the set of rational numbers using set builder notation. So the set of rational numbers, here it is. There's a special symbol for this set also. The set of rational numbers, they use this special Q for it, the set of rational numbers. And it's the set, and the variable looks like this. It's a fraction, P over Q. Then there's the vertical bar. Then it describes P and Q are both elements of the integers. Remember, this is the symbol for the integers. So P and Q are both integers, and Q is not equal to 0. Q is not equal to 0. So this describes the set of numbers that we call the rational numbers. Basically, fractions where the top and bottom of the fractions are integers, but the bottom is not 0, because you can't divide by 0. All right, so these are infinite sets. It turns out that infinite sets also have cardinality. So, a set with the same cardinality as the set of natural numbers, remember n, that set of natural numbers, is called a countably infinite set. So it turns out there are different kinds of infinity. Countably infinite is a smaller infinity. It's one of the smaller ones here. So countably infinite. And let's take a look at this set. This is the set of natural numbers. Any set that has the same number of elements as the set of natural numbers is said to be countably infinite. So here are some countably infinite sets. We discussed this one. The set of integers. It turns out that the set of integers has the same number of elements as the set of natural numbers. How, you ask? It seems as though the set of integers has at least twice as many elements as the set of natural numbers, because, I mean, not only do you have the natural numbers as a part of the set of integers, but you have the opposites and zero. So you have the negatives and zero included here. But it turns out that if you write the set of integers this way, so you start with 0, then you have negative and positive 1, then negative and positive 2, then negative and positive 3, and negative and positive 4, and so forth. You can actually count them with these natural numbers. So you can count how many integers there are, beginning with 0, then negative and positive 1, negative and positive 2. You can go all the way up to negative positive infinity, and there's only an infinity of numbers there. So it turns out that these two sets have the same number of elements. They both just have an infinite number of elements, and it's the same number. It's actually the same infinity. This infinity has a name. So what I'm saying here is that the cardinality of the natural numbers, or the number of elements that are in the natural numbers, is the same as the number of elements in the integers. I can count the number of integers. And the name of that cardinality is this, Aleph null. This is the smallest infinity. The smallest infinity, Aleph null. So the cardinality of a countably infinite set is Aleph null. All right, let's take a look at one last set here. One last countably infinite set. This is the set of rational numbers. So basically, you take this set of integers and you make fractions out of them, and you make sure that the bottom of those fractions is never equal to 0. This is the set of fractions made out of integers, where the bottom can't be 0. This is what most people consider to be fractions. So it turns out that this set is also countably infinite. There are just as many of these as there are natural numbers. Let me show you. We can make this table where along the rows of the table, we're counting first 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, 1/9, and so forth. Then 2 2/2, 2/3, 2/4, 2/5, 2/6, 2/7, and so forth. Then 3 3/2, 3/3, 3/4, and so forth. You can continue doing this all the way to infinity. So you can continue doing this forever, basically, in both directions. Like, basically, you could even count down 1/3, 2/3, 3/3, 4/3, 5/3, 6/3, 7/3, 1/4, 2/4, 3/4, 4/4, 5. So basically, this would represent every single possible ratio or fraction of integers, because I have all the numerator integers going across here. So this represents all the numerators. 1 as a numerator, 2 as a numerator, 3 as a numerator, 4 as a numerator. And this, the columns represent all the possible denominators. 1 as a denominator, 2 as a denominator, 3 as a denominator, 4 as a denominator. So if you make this chart, it basically represents every possible fraction you could possibly make where the numerator or denominator is not 0. And it turns out that if you try to count these this way, 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, you would continue with all these fractions that have numerators of 1 forever, and you'd never get to the second row. You'd never get to start counting with the 2's. Or if you count this way, 1/2, 2/2, 3/2, 4/2, 5/2, 6/2, 7/2, 8/2, you'd continue counting along this column forever, and you'd never get to the next column. So if you continue counting either straight along a row or straight along a column, you can't actually count these the same way you would count the natural numbers. But if you follow this pattern right here, you can actually count these fractions. So you start with 1, 2, then you go to 1/2, 1/3, and then you go to 2/2, 3, then you go to 4, then 3/2, then 2/3, then 1/4, then 1/5, then 2/4. So basically you're going down every diagonal, then you're slipping down to the next row and going up the next diagonal, slipping over to the next column, then going down the next diagonal, slipping down to the next row, going up the next diagonal, and eventually you'll hit every single one if you keep going like this. So you can write all these out and you'll hit every single fraction. Well, if you can hit every single fraction, that means that you can actually count every single fraction. And it turns out that the rational numbers have the exact same number of elements as the natural numbers. So the number of elements in the natural numbers is the same number of elements in the integers, is the same number of elements in the rational numbers, which is this thing that we call Aleph null. It's the smallest infinity. The smallest infinity. All right, so we have all these countably infinite sets. These are some countably infinite sets. I want to introduce you, before I go here, to one last set, the set of real numbers, the set of numbers that are on the number line. So the set of all the numbers on the number line is actually an example I want to give of an uncountable set. In the way that we counted the integers and counted the rational numbers, there's no way of actually counting the real numbers. The real numbers is not the same cardinality as the set of natural numbers. The set of real numbers, the set of numbers on the number line, actually has a cardinality of Aleph 1. So these three sets all have cardinality Aleph null. They're called countably infinite. This set, the set of real numbers, is uncountably infinite. You can't count the real numbers.